The world has edges. Some are drawn on maps. Others exist where conditions become so absolute that presence itself feels like trespass. At the bottom of our planet lies a surface that reflects nothing but itself, white extending into white, cold that doesn't feel like temperature but like the absence of everything temperature protects. Beneath that surface is another world entirely. Not a frozen wasteland, not an empty void, but a landscape of valleys and peaks, rivers that flow in total darkness, lakes that have never seen sky. All of it sealed beneath ice so thick that standing on top of it means standing on top of time itself. The weight above is measured not in tons but in the compression of millennia, every snowflake that fell and stayed, every winter that refused to end, layer upon layer upon layer. Some of that ice formed before humans learned to write, some before we learned to speak, some before our species existed at all. And beneath all of it something continues. Water moves, stone shifts, chemistry unfolds at a pace that makes patience look like urgency. We've mapped the ocean floor, we've photographed distant galaxies, we've sent machines to other planets. But what lies directly beneath the South Pole remains largely unknown. Not because we lack curiosity, not because the technology doesn't exist, but because the ice itself creates a kind of impossible boundary. A threshold that destroys what crosses it, a silence that swallows sound, a darkness that exists not from lack of light but from the total inability of light to reach it. This is not a story about what we've found. It's a story about what resists being found. About the space between wanting to know and being able to touch. About the difference between a question and an answer. About why some frontiers remain frontiers not because we've stopped trying, but because the world itself says not yet. The descent begins here, not with a step but with understanding. That to explore beneath the South Pole's glaciers means first accepting that the ice has its own terms, its own timeline, its own way of keeping what it holds. Welcome to Info Jungle. If you enjoy calm, thoughtful documentaries about the natural world, consider subscribing. We create these videos to help you learn and relax at the same time. Let the journey continue. Imagine standing in a place where your footsteps make no sound that carries, where the air is so cold it feels solid against your skin, where looking in any direction reveals the same endless plain. This is the surface of East Antarctica, the highest desert on Earth, a plateau of ice that rises more than 3 kilometers above sea level. The snow here doesn't melt, it accumulates, year after year after year. Each flake that lands becomes part of a structure, so massive it warps the Earth's crust beneath it. Scientists measure this weight in gigatons, numbers so large they become abstract, but the effects are visible in ways that numbers never capture. The continent of Antarctica sits lower now than it did before the ice arrived. The bedrock beneath has been pressed down like clay under a thumb. Valleys that once stood at sea level now rest hundreds of meters below it. Mountains that would rival the Alps, if exposed, remain buried under frozen mass. This isn't geology frozen in place. It's geology being actively reshaped by the simple, persistent presence of ice. The ice sheet moves, not quickly, not visibly, but constantly. It flows outward from the interior toward the coasts, driven by its own weight, by gravity pulling on mass that has nowhere else to go. The movement happens at the scale of meters per year, sometimes faster, sometimes slower, always ongoing. Beneath that motion lies the landscape no one has walked. Radar has shown us shapes, echoes suggest form, satellite measurements detect variations in thickness and density. But seeing through ice is not the same as seeing. The signals we send down come back altered, bent by temperature, scattered by pressure, distorted by the very thing we're trying to penetrate. What emerges is a map built from inference, from educated guessing, from comparing thousands of partial readings and hoping they align. In some regions, the ice is so thick that radar can't reach bottom. The signal fades before it returns. What lies there remains unknown, not because we haven't tried, but because the ice simply absorbs our attempts. This weight creates something unexpected. At the base where ice meets rock, the pressure becomes so intense that the freezing point of water drops. Ice that should be solid begins to melt, just slightly, just enough. This melt water doesn't freeze again immediately. Instead, it pools, it flows, it carves channels through the bedrock beneath. The same weight that seals the world away also creates the conditions for liquid to exist where none should. Darkness and pressure and isolation, these are the constants. Yet within them, water moves, and where water moves, chemistry follows, and where chemistry unfolds, life might persist. The weight of the ice is not just physical, it's temporal. To drill through, it means drilling through time. Each meter deeper reaches air from earlier eras, carbon dioxide levels from centuries past, dust from volcanic eruptions long forgotten. The ice remembers. It holds the atmosphere of a planet that looked different than it does now, forests where deserts exist, rivers where ice has settled. All of it compressed into layers so fine that a single core sample can contain 10,000 years of climate data. But that memory comes at a cost. The same conditions that preserve also prevent access. The same weight that creates stability makes disturbance catastrophic. Every drill that enters leaves a wound the ice wants to heal. Every borehole begins closing the moment it's made. The ice flows inward to fill the space, to restore equilibrium. This is not hostility, it's physics. The weight doesn't care about our instruments. It responds only to imbalance, and drilling creates imbalance. So the ice reclaims, it crushes, it freezes what touches it, it dissolves presence back into absence. What we call exploration here is really negotiation. We ask permission through preparation, through sterilization, through designs that anticipate failure. And even then, the ice decides. Some missions succeed, data returns, samples emerge. Others vanish into the white, instruments seized by pressure, cables frozen in place, transmissions ending mid-sequence. The weight of absence is measured not in what we've lost, but in what was never reachable to begin with. Beneath the South Pole lies a geography that exists primarily as data, as numbers on screens, as three-dimensional models that rotate in virtual space. The real landscape remains untouched. Not because it's sacred, not because we've declared it off limits, but because the mass above it creates a barrier more absolute than any human boundary ever could. We stand on top of something immense, something ancient, something that continues without acknowledgement of our presence. The weight presses down, the ice flows, and beneath it all the hidden world persists in its own terms. Sound behaves differently here. In the dry, cold air of the Antarctic plateau, voices don't carry the way they should. Words fall flat. Distance swallows them before they can become echoes. It's an acoustic phenomenon that happens when air lacks moisture, when cold makes molecules sluggish, when nothing exists to reflect or amplify. But beneath the surface, sound takes on another quality entirely. Ice conducts vibrations. Seismic waves travel through it faster than through water. Each tremor, each shift, each crack sends signals rippling outward. Scientists use this. They place sensors on the ice and listen, not for noise but for patterns, for the language of stress and release. When glaciers move, they groan. When pressure builds, they crack. When hidden water flows, it creates friction that hums at frequencies below human hearing. These sounds, invisible to us, paint pictures of what lies beneath. Seismographs detect ice quakes, tiny earthquakes within the glacier itself. Each one marks a moment when frozen structure adjusts to the weight bearing down on it. The data streams back as waveforms, peaks and valleys on a graph, evidence of motion in a place that seems perfectly still. By studying these patterns, researchers can map the interior. They can identify where ice flows quickly and where it barely moves, where melt water pools and where pressure builds. But the echoes don't always return cleanly. Some get lost in the noise of wind and machinery. Others scatter through layers of varying density. The ice isn't uniform, it's stratified, compressed snow from different eras, frozen rain from ancient storms, dust trapped in crystals. Each layer bends sound differently. So what comes back is a puzzle, a fractured signal that must be decoded, interpreted, cross-referenced with other measurements. In some areas, the echoes fade entirely. Deep zones where the ice is so thick or so old that vibrations can't penetrate. Regions where the base remains invisible even to the most sensitive instruments. These blank spots on the map are not empty, they're simply beyond reach. The technology exists, the will exists, but the ice absorbs more than we can send. And so those areas remain mysteries, known to exist but unknowable in detail. There's something humbling about that. In an age where we expect answers within seconds, the Antarctic interior reminds us that some information arrives slowly, or not at all. The echoes we do receive tell us extraordinary things. They've revealed mountain ranges buried for 30 million years, peaks sharp as if carved yesterday, valleys deep enough to swallow cities. They've shown us how the bedrock undulates, how it rises and falls in waves, how the weight of ice has carved it into shapes no surface geology would produce. And they've confirmed what thermal readings suggested. That beneath the ice water exists, not as solid frozen mass, but as liquid. Lakes the size of countries, rivers that flow through channels carved in stone, a hydrological system operating in complete darkness. The echoes trace these features. They show where water accumulates, where it drains, where it connects distant reservoirs into networks that span the continent. But even with all this data, the picture remains incomplete. Because echoes can only tell us shape. They can't tell us chemistry. They can't reveal what lives in those waters. They can't measure the age of sediments at the bottom. For that we need direct access. And direct access means drilling. Which brings us back to the problem of weight. Every borehole is an intrusion. Every probe a potential contaminant. The same echoes that guide us also warn us. They show how fragile the balance is, how quickly conditions change, how easily we could alter what we're trying to study. So the work proceeds with caution. Teams drill slowly. They use hot water instead of mechanical bits. They sterilize everything that touches the ice. And they listen. Between each phase of drilling they stop and send signals down, checking to see if anything has changed, if pressure has shifted, if the borehole is collapsing. The echoes tell them whether to continue or retreat. Sometimes they fade before reaching target depth. The ice closes in, the path disappears. Other times they return altered, changed by something unexpected, a pocket of air, a layer of sediment, a fluctuation in temperature. Each anomaly becomes a clue, not just about what's there, but about how the ice itself behaves, how it responds to disturbance, how it maintains its structure despite the constant stress. The fading of echoes is not failure. It's information. It tells us where our limits are, where the ice decides we've gone far enough. And in respecting those limits, we preserve what remains. The hidden world continues to exist because it's shielded, protected not by choice, but by the sheer physical reality of its encasement. We listen to what the ice allows us to hear. We map what the echoes reveal. And we accept that some regions will remain silent, not because they're empty, but because they exist in a register we can't yet reach. Cold is not the absence of heat. It's the presence of stillness. Molecules moving so slowly that energy itself seems paused. At the South Pole, the average temperature hovers around -50 Celsius. During winter, it drops lower, sometimes below -70. At those temperatures, exposed skin freezes in seconds. Breath crystallizes before it leaves your mouth. Metal becomes brittle enough to shatter. But that's just the surface. Beneath the ice, the temperature follows different rules. The deeper you go, the warmer it becomes. Not warm in any comfortable sense, but less cold, hovering just below the freezing point of water. This gradient exists because of two forces. From above, the weight of the ice creates pressure. Pressure generates heat through friction, through the slow grinding of crystal against crystal as the glacier flows. From below, the earth itself radiates warmth. Geothermal energy rising from the mantle, not enough to melt rock, but enough to keep the base of the ice sheet from freezing solid. The result is a thin layer where conditions allow liquid water. Not flowing freely, not pooled in open caverns, but seeping through cracks, filling microscopic spaces between ice and stone. This is where the hidden lakes exist. Lake Vostok, Lake Willans, Lake Ellsworth. Each one sealed beneath kilometers of ice, each one at a temperature that shouldn't support liquid. Yet they persist, because the ice above insulates them, because pressure lowers the freezing point, because geothermal heat provides just enough energy to maintain the balance. These lakes are not static. They breathe in geological time, filling when meltwater arrives from upstream, draining when channels open downstream. The cycle happens over years, sometimes decades, detected only by satellite measurements showing the ice surface rising or falling by meters. The temperature of these lakes hovers between -3 and 0 Celsius, cold enough to kill most life, but not all. Microbes have been found in samples taken from subglacial water, organisms adapted to darkness and pressure, to cold that would crystallize the cells of surface creatures. They survive by chemistry, feeding on minerals dissolved from bedrock, metabolizing sulfur and iron instead of sugar, existing in a kind of suspended animation where reproduction happens over months instead of hours. These are not thriving ecosystems, they're minimal ones. Life reduced to its most essential functions. But they prove something profound. That habitability is not about comfort, it's about possibility. If microbes can persist in Antarctic subglacial lakes, then life might exist in even harsher environments. On Europa, on Enceladus, on worlds where sunlight has never penetrated. The temperature gradient also creates danger. When drilling through ice, the warmth of machinery can destabilize the borehole. Melt water forms around the drill bit, then refreezes instantly when the drill pulls back. This seals instruments in place, locks cables, closes paths. The ice uses temperature as a weapon, not intentionally, but as a consequence of its physics. Every degree matters. Too warm and the borehole collapses. Too cold and equipment fails. The range of tolerance is narrow. Teams must maintain precise thermal control, heating water to exactly the right temperature, circulating it through the drilling system, monitoring every fluctuation. Even then, unexpected thermal currents can ruin months of preparation. A pocket of warmer ice, a layer that conducts heat differently, a sudden influx of geothermal energy. Any of these can shift conditions enough to make the drill inoperable. The temperature of time is measured in patience, in how long ice takes to form, in how slowly it releases what it holds. Each layer of the ice sheet corresponds to a specific year, sometimes a specific season. By drilling cores and measuring isotopes, scientists can reconstruct temperature records going back 800,000 years. They can see when the planet warmed and cooled, when carbon dioxide spiked and fell, when volcanic ash darkened skies across hemispheres. But reading those records requires keeping the ice frozen. If a core warms during extraction, the data degrades, gases escape, crystals deform, the timeline blurs. So samples are kept at -20°C from the moment they're collected, transported in refrigerated containers, stored in freezers that never fluctuate. The temperature must remain constant, because time stored in ice is fragile. It doesn't decay the way organic material does, but it can be lost through carelessness. Every degree of warming erases part of the record. This is why exploration here feels so delicate. We're not just dealing with extreme conditions, we're handling history. The ice beneath the South Pole contains information that exists nowhere else. Air from when humans first learned to farm, climate data from before civilizations rose, chemical signatures of a planet in balance. And all of it depends on temperature staying exactly where it is. But the planet is warming. Surface temperatures in Antarctica have begun to rise, not dramatically, not uniformly, but measurably. The gradient that kept the ice stable for millions of years is shifting. What was frozen now melts, what was sealed now opens. The temperature of time is changing, and with it, the accessibility of what lies beneath. Some researchers see this as opportunity. As ice thins in certain regions, drilling becomes easier. Lakes that were unreachable might become accessible. Others see it as loss. Because what we gain in access, we lose in preservation. The pristine isolation of subglacial environments depends on cold, on pressure, on stability. When those conditions change, the ecosystems change. Water that once stayed separate mixes. Organisms that evolved in isolation encounter new chemistry. The temperature shifts and an entire world adjusts, whether we're ready to understand it or not. The thermometer at the South Pole Station reads numbers that seem impossible. -60, -70, -80 during the darkest months. But those numbers only describe the surface. Beneath the ice, a different temperature exists. One that allows liquid, that permits chemistry, that enables persistence. The cold we experience is not the cold that defines the hidden world. Down there, temperature is measured in gradients, in the space between frozen and flowing. And that space, however narrow, is where everything continues. There are places on Earth where darkness is temporary. Night falls and morning follows. Caves have entrances. Deep ocean trenches eventually rise toward light. But beneath Antarctica's glaciers, darkness is permanent. not the darkness of shadow, the darkness of burial. No photon has reached these spaces for millions of years. No ray of sunlight has touched the bedrock. No glow of bioluminescence exists to break the black. This is absolute darkness, the kind where the concept of seeing becomes meaningless. Yet within this void structure exists valleys carved by water that no longer flows above ground, ridges shaped by tectonic forces older than the ice, chambers where lakes collect in depressions worn smooth by time. The architecture beneath the South Pole is not random. It follows patterns. Water flows downhill even when the gradient is measured in millimeters per kilometer. Sediment settles in layers that record the pace of deposition. Ice above presses down in ways that shape the rock below. Radar imaging shows us outlines. The Gamburtsev Mountains rising like ghosts from the bedrock, peaks that would stand 3 kilometers high if exposed. The Aurora Basin sinking below sea level, a depression large enough to contain an ocean. The Bentley subglacial trench dropping even deeper, the lowest point on Earth not covered by water. These features were discovered not by exploration, but by echo, by sending radio waves down and measuring what came back. The signals revealed topography, elevation, the shape of a continent hidden in darkness. But shape is not substance. We know there are mountains, but not what stone they're made of. We know there are valleys, but not what sediment fills them. The architecture we've mapped is incomplete. A sketch rather than a blueprint. In some regions, the darkness is structured by water. Subglacial lakes sit in basins where the bedrock dips. Their surfaces are flat because liquid always seeks level. The largest of these, Lake Vostok, stretches over 14,000 square kilometers, larger than some small countries. Its depth reaches more than a kilometer in places, and it exists entirely enclosed, sealed by ice above, bounded by rock on all sides. The water within has been isolated for between 15 and 25 million years. No mixing with surface systems, no replenishment from rainfall, no connection to the ocean. Just pressure and darkness and chemistry unfolding at its own pace. The architecture of this darkness includes channels, pathways carved through the bedrock where water flows from one lake to another. These channels are not like surface rivers. They don't rush or tumble. They exist as thin films, as fractures filled with liquid, as passages barely wider than centimeters. But collectively, they form a network, a hydrological system that redistributes melt water across the continent. When one lake fills, it drains through these channels to another. The pressure equalizes, the system balances. Satellites detect this motion by measuring changes in ice surface elevation. When a lake drains, the ice above it sinks. When another fills, the ice rises. These movements happen over months or years, slow enough that the ice can adjust without fracturing. The channels themselves remain invisible. We infer their existence from the motion they cause. They're part of the architecture we know must be there, even though we've never seen them directly. The rock beneath the ice is not uniform. In some areas, it's ancient crystalline basement rock, granite and gneiss older than most mountain ranges. In others, it's sedimentary, layers of sandstone and shale compressed over eons. The type of rock determines how water moves. Porous stone absorbs it. Dense stone forces it to flow along surfaces. These differences create the hidden topography. They shape where lakes form and where channels develop. The architecture of darkness is written in geology as much as geography. Every mineral present affects the chemistry of the water. Every crack in the bedrock provides a pathway. And because we can't see any of this directly, we must reconstruct it from traces. From the composition of melt water that seeps to the surface, from magnetic anomalies detected by satellites, from gravity measurements that show where mass is distributed. The picture that emerges is magnificent. A landscape as complex as any on the surface, but inverted. Where the surface has peaks exposed to sky, the subglacial world has valleys buried in ice. Where the surface drains toward oceans, the subsurface collects in isolated basins. It's a mirror geography, one that exists only because the weight above allows it. In this darkness, life adapted. Not in abundance, not in diversity, but in persistence. Microbes found in Lake Whillans live at densities measured in thousands per milliliter. Not millions, not billions. Thousands. They cluster near the sediment interface where minerals are most accessible. They metabolize compounds that require no light. They reproduce slowly enough that generations span years. Their architecture is cellular. Simple organisms with minimal genetic complexity, built to endure rather than thrive. But they form communities. Networks of bacteria sharing chemical signals, distributing nutrients through biofilms, creating microenvironments within the larger darkness. This is not a barren void. It's a sparse ecosystem, one that operates on principles unlike any surface environment. The architecture of darkness includes time. Sediment layers at the bottom of subglacial lakes contain records going back millions of years. Pollen from forests that once grew here, diatoms from oceans that covered the continent, organic molecules from life that predates the ice. These layers are undisturbed. No currents to mix them, no bioturbation from burrowing organisms, no weathering from exposure. Just steady accumulation. Particle by particle, year by year. The architecture here is stratigraphic. Built vertically, each layer distinct from the one above and below. To drill through these sediments would be to drill through time. To sample them would be to touch a record preserved better than any fossil. But reaching them without disturbing them is nearly impossible. The act of drilling creates currents. The heat from equipment alters chemistry. The presence of modern materials introduces contamination. So the architecture remains largely intact. Studied from a distance, understood through inference. The darkness protects what it holds. Not through active defense, but through sheer inaccessibility. In some ways, the architecture beneath the South Pole resembles cave systems. Interconnected chambers, channels linking them, water flowing through in slow motion. But caves have entrances. This system has none. It's entirely enclosed. A world that exists only because the weight above creates the conditions for it. We can map its shape, we can model its chemistry, we can predict how it behaves. But we cannot walk through it, cannot shine light into its spaces, cannot touch its walls. The architecture of darkness remains beyond physical reach, a geography known only through abstraction. And perhaps that's fitting, because some places are meant to be understood rather than visited. Some structures reveal themselves through pattern rather than presence. The hidden continent beneath Antarctica is one of those places. Built by forces we can measure, shaped by time we can calculate, existing in darkness we can only imagine. Its architecture stands complete, whether we ever see it or not. Water has memory, not consciousness, not thought, but a kind of chemical record of everywhere it's been. The water beneath Antarctica's glaciers carries traces of its journey. Isotopes that reveal temperature during formation, dissolved minerals that identify the rock it flowed through, gases trapped when it froze then melted again. Each molecule is a tiny archive. When scientists finally managed to sample water from Lake Whillans, they found something unexpected. The water was not pure. It contained sediment, organic carbon, DNA. Not from surface contamination, but from the lake itself. The genetic sequences belong to organisms that don't exist anywhere else. Bacteria adapted to extreme pressure, archaea that metabolize methane, unknown microbes with genes unlike anything in existing databases. The water remembered the evolution that happened within it. Over millions of years, in complete isolation. These organisms didn't arrive recently. They've been there since before the ice sealed the lake. Or they evolved from ancestors that were. The water holds the story of their adaptation. In the chemistry of their metabolism, in the compounds they produce, in the way they've learned to survive without light. When researchers analyzed the sediment, they found traces of ancient pollen. From plants that grew in Antarctica 30 million years ago. Before the ice sheet formed, when the continent was temperate. The water remembered forests. Not through biological preservation, but through molecular remnants. Fragments of cell walls, traces of lignin, chemical signatures of photosynthesis. All of it dissolved into the water, carried through the subglacial system, deposited in layers that accumulated over eons. The memory is not perfect. Time degrades complex molecules, pressure alters structures, chemistry slowly breaks down what once was whole. But enough remains. Enough to reconstruct what existed, to understand how the continent transformed. The water beneath Antarctica doesn't just remember the past. It records the present. Every change in temperature leaves an isotopic signature. Every shift in ice flow alters the mineral content. Every earthquake sends vibrations through the system. The water responds to all of it. And in responding, it creates a chronology. One that scientists are only beginning to read. The challenge is accessing that memory without erasing it. Drilling introduces modern water. Sampling disturbs the equilibrium. Analysis consumes what little material is available. So the work proceeds in fractions. A few milliliters from one location, a small core of sediment from another. Each sample is divided among research teams, each fraction analyzed for different properties. The goal is to extract maximum information from minimal intrusion. To let the water tell its story without forcing it to speak too loud. Some of the most intriguing findings come from isotopic analysis. Oxygen isotopes in ice cores reveal temperature variations over 800,000 years. But oxygen isotopes in subglacial water tell a different story. They show mixing between melt water and ancient liquid, between ice formed during warm periods and ice from glacial maximums. The ratios don't match surface patterns. They suggest that the water beneath has its own circulation, its own timeline independent of what happens above. The memory it carries is not synchronous with atmospheric records. It's offset, delayed, filtered through the slow motion of the glacier. By the time melt water reaches a subglacial lake, it might carry information from ice that formed thousands of years earlier. The water remembers, but on a lag. This creates complexity for climate scientists. They can't simply correlate subglacial chemistry with surface conditions. They have to account for the time it takes for water to travel, for pressure to alter its composition, for reactions with bedrock to change its signature. The memory is there, but reading it requires translation. Another form of memory exists in dissolved gases. When water freezes, it expels gases into tiny bubbles. When it melts, those gases dissolve again. The concentration and composition of gases in subglacial water reflect the atmosphere at the time the ice originally formed. Nitrogen, oxygen, carbon dioxide, methane, all present in ratios that correspond to specific eras. By measuring these, researchers can determine when the ice above the lake was last exposed to open air. For Lake Vostok, that date is approximately 15 million years ago. The water remembers an atmosphere from the Miocene epoch, when carbon dioxide levels were higher, when global temperatures were warmer, when Antarctica looked nothing like it does now. That memory is locked in liquid form, waiting for the rare moment when a borehole penetrates deep enough to sample it. The sediments at the bottom of these lakes hold even older memories, layers that formed before the ice arrived. When rivers flowed across the continent, when rain fell on exposed rock, when vegetation covered the landscape, these sediments contain fossilized pollen and spores, evidence of plant species that thrived in temperate climates. Southern beech trees, ferns, mosses, all buried beneath kilometers of ice, preserved in the darkness. The water that now covers these sediments has absorbed some of their chemistry. Organic molecules leached into the liquid, minerals dissolved from the surrounding matrix. The lake water carries the signature of a continent that no longer exists above ground. It remembers warmth, it remembers life, even though both are gone from the surface. There's something profound about this. The realization that water can hold information across geological time, that the same molecules cycling through the subglacial system have been there since before the ice. They've witnessed the entire transformation. From forest to desert, from warmth to freeze, from exposure to burial. And they've recorded it. Not in words, not in images, but in chemistry, in ratios of isotopes, in concentrations of dissolved solids, in the presence of compounds that shouldn't exist in such an environment. The memory is fragmented, pieces scattered across multiple lakes, traces diluted by millions of years of circulation. But it's recoverable. If we're patient, if we're careful, if we treat each sample as the precious archive it is. The water beneath the South Pole doesn't just remember Earth's past. It might hint at possibilities beyond it. The chemistry found in Lake Whillans includes compounds similar to those detected on Europa, Jupiter's ice-covered moon. The metabolic pathways used by subglacial microbes resemble those predicted for life in subsurface oceans elsewhere. If organisms can survive in Antarctic darkness, they could survive on other worlds. The water remembers how. It carries the blueprint for extreme adaptation, for persistence in conditions that seem impossible. This makes Antarctica's subglacial lakes more than scientific curiosities. They're analogs, test cases for understanding habitability throughout the solar system. The memory stored in that water might help us interpret data from distant moons, might guide the design of missions to explore beneath ice shells light years away. But only if we can read the memory correctly. Only if we don't erase it through careless exploration. Every time a drill enters the ice, there's risk of introducing contamination, of altering pressure, of mixing systems that should remain separate. The water will remember that too. It will incorporate whatever we bring. And future scientists trying to read its record will have to account for our presence, for the fingerprints we leave. This is why protocols are so strict, why every instrument must be sterilized, why drilling fluids must be pure. The memory of the water is irreplaceable. Once compromised, it can't be restored. We get one chance to read it correctly. And that chance depends on restraint, on recognizing that some memories are too valuable to risk. The water beneath the South Pole holds secrets we're only beginning to access. Stories written in molecules, histories encoded in chemistry, possibilities suggested by the presence of life where none should be. It remembers a planet we never knew. It preserves a record we can barely read. And it continues its slow circulation through channels we can't see, past organisms we're only beginning to understand, carrying information forward into whatever comes next. The water remembers, and in that memory lies both warning and possibility. A record of how worlds change and how life adapts when they do. There's a graveyard beneath the ice, not of bones, of instruments, probes that descended and never returned, cables that froze in place, sensors that transmitted briefly then went dark. Each one represents a mission, years of planning, months of preparation, millions of dollars in technology, all consumed by the environment they tried to measure. The Antarctic interior is efficient at destruction, not through violence, through persistence. Cold that makes metal brittle, pressure that crushes protective casings, ice that flows around intrusions and seals them away. Every machine sent into this environment enters a negotiation it's designed to lose. The question is never if it will fail, only when. And what data it can transmit before silence returns. Engineers who design Antarctic equipment speak in terms of survival time. Hours for simple instruments, days for well-insulated ones, months if conditions are favorable and luck holds. But favorable conditions are rare. The base of the ice sheet operates at pressures exceeding 400 atmospheres. Temperatures hover just below freezing but fluctuate unpredictably. Chemical interactions between water and metal corrode seals. Sediment clogs filters. And the ice itself moves, slowly but inexorably, grinding against anything fixed in place, deforming boreholes as it flows. A probe anchored today might be crushed tomorrow, not by sudden impact, by gradual compression as the ice reclaims the space. The first attempts to reach subglacial lakes ended in failure. Drills that stopped halfway down when lubricants froze. Boreholes that collapsed before instruments could be lowered. Sensors that malfunctioned the moment they touched water. Each failure taught something. About thermal management, about pressure compensation, about the impossibility of controlling every variable. The environment doesn't cooperate. It doesn't care about careful planning or precise engineering. It responds only to physics. And physics here favors the ice. Modern instruments are designed with redundancy. Multiple sensors in case some fail, backup power systems, communication channels that switch frequencies if one stops working. But redundancy has limits. When pressure crushes a housing, no backup prevents it. When ice flows around a cable and shears it, no secondary line helps. The machines fall silent, and the silence is absolute. No error message, no final transmission, just the sudden absence of signal. teams monitoring from the surface wait, sometimes for hours, sometimes for days, hoping the instrument will revive, that a temporary glitch will resolve. But usually the silence persists, and eventually they accept what they already knew, that another machine has been added to the inventory beneath the ice. One more artifact in a collection no one will ever see. The psychological weight of these losses affects the people involved. Years of work to design an instrument, months of logistical planning to transport it, weeks of careful drilling to create the access point, then minutes or hours of data. Before silence, it's difficult not to feel the futility. But those who continue understand something crucial, that even failed missions contribute. They show where the boundaries are, what the ice will tolerate, what it won't. Every silent machine refines our understanding of the limits. And those limits matter, because they define what's possible. Not theoretically, but practically. Some research stations keep logs of lost equipment, inventories of what's been left behind, drill bits abandoned in boreholes, sensors trapped in ice, cables severed by pressure. The lists grow longer each year, not because teams are careless, but because the work itself demands risk. To explore beneath the ice means accepting that some tools will be sacrificed. That access comes at the cost of equipment, and sometimes the cost is too high. Projects are abandoned mid-operation, when the rate of instrument failure exceeds the rate of data collection, when it becomes clear that the ice is winning faster than expected. The decision to stop is never easy, but it's often necessary, because continuing means losing more, with no guarantee of gaining anything. The silence that follows these decisions is different. Not the silence of equipment failure, but of human choice. The recognition that some frontiers resist crossing. That persistence without wisdom becomes waste. One of the most expensive failures happened during an attempt to reach Lake Ellsworth. A British team spent over a decade planning the mission. They designed a hot water drill system capable of penetrating 3 kilometers of ice, built a mobile drilling rig that could operate in extreme cold, tested every component in climate chambers. The operation began successfully. The drill descended, boreholes formed. But partway through the main shaft a coupling failed. The circulation system lost pressure. Without constant flow, the borehole began to freeze. The drill became stuck. Attempts to restart failed. The mission was suspended. Years of preparation, millions in funding, and no samples retrieved. Just another drill bit buried in the ice. The team didn't call it failure. They called it learning. But the silence that followed spoke louder than any data could have. It said that even the best preparation can't guarantee success. That the ice doesn't negotiate. Some instruments fail because they're pushed beyond design limits. Others because the environment itself changes unexpectedly. A pocket of warmer ice, a layer with different density, a sudden influx of melt water. Variables that models can't predict. That sensors can't detect until it's too late. The machines fall silent because they're operating at the edge of the possible, in conditions no laboratory can fully replicate. And when they do fail, they take their data with them. Partial transmissions that end mid-sequence. Readings that show anomalies then stop. Mysteries that will never be solved because the instrument that detected them is gone. This creates frustration. but also humility. The realization that we're working in a place that doesn't accommodate human timelines, that measures success in geological patience, not quarterly reports. The machines that do survive become almost legendary. Sensors that transmit for months beyond their expected lifespan. Probes that withstand pressures they shouldn't. Cables that remain intact despite the ice flowing around them. These exceptions are studied carefully to understand what they did right. What combination of design and luck allowed them to persist. But the lessons are hard to replicate because survival often comes down to factors beyond control. Being positioned in a stable zone, avoiding a pressure gradient, missing a fracture by centimeters. The machines that survive are often just fortunate. Not better, just luckier. And luck is not a strategy. There's something almost poetic about the graveyard beneath the ice. A collection of human ambition buried in darkness. Each instrument a testament to curiosity. Each silent transmission a reminder of limits. The ice preserves them as it preserves everything else, sealing them away, maybe for millions of years, until the glaciers retreat or collapse. And then perhaps someone will find them. Artifacts from an era when humans tried to understand what lay beneath. When we built machines to penetrate the impossible, and learned that some impossibilities remain. For now, the graveyard grows. Each season adds new members. Probes that descended with hope, sensors that promised revelation, all falling silent in their turn. The ice accepts them without ceremony, flows around them, compresses them, absorbs them into its slow advance toward the sea. And above on the surface, teams pack up their equipment, update their logs, and begin planning the next attempt. Because the silence of machines doesn't end curiosity. It refines it, teaches us to build better, to expect less, to value each fragment of data as the precious thing it is. The machines fall silent, but the work continues. Quieter now, more careful, with the understanding that every instrument sent down might be the last to return anything at all, and that the silence waiting below is patient, absolute, willing to wait as long as necessary, for the next machine, and the next, until we finally learn to listen without needing to touch. There's a thought experiment that happens in quiet moments. What if we could reach the subglacial lakes without drilling? Without boreholes or probes or chemical contamination? What if we could simply see through the ice? Watch the water move, observe the microbes, study the sediments, all without leaving a mark. Would we do it? Or would we recognize that even observation changes what we observe? The answer matters, because it defines whether our exploration is discovery or intrusion. Antarctica forces this question more urgently than anywhere else. The continent exists under international agreement, protected from exploitation, reserved for science, governed by cooperation rather than ownership. It's one of the few places where humanity chose restraint, where we decided that some regions should remain beyond national claim, beyond resource extraction, beyond everything except understanding. But even understanding has weight. Every sample taken removes material that can never be replaced. Every borehole creates a pathway that didn't exist. Every instrument introduces modern material into ancient systems. The question becomes how much change is acceptable in pursuit of knowledge. There's no easy answer. Scientists debate it constantly. Some argue that the importance of the data justifies careful intrusion, that what we learn could help us understand life on other worlds, could predict how Earth's climate will respond to warming, could reveal biological mechanisms we've never encountered. The potential benefits are enormous. Others counter that the environments beneath the ice are irreplaceable, that once contaminated, they can never be studied in their original state, that our presence, however careful, leaves permanent marks, that some places should remain untouched, not because we can't reach them, but because reaching them destroys what makes them valuable. Both positions have merit. The tension between them defines modern Antarctic research. When Russian teams first drilled into Lake Vostok, the controversy was intense. Environmental groups warned that the drilling fluid contained chemicals that would pollute pristine water, that modern bacteria on the drill bit would introduce organisms into an ecosystem sealed for millions of years, that the pressure release when the drill broke through would mix layers that had remained separate. The scientists proceeded anyway, arguing that the knowledge gained outweighed the risks, that protocols were in place to minimize contamination, that the opportunity to study such an environment was too important to miss. The samples they retrieved showed life, DNA sequences unlike anything previously cataloged, evidence of metabolic pathways adapted to extreme conditions. It was extraordinary. But the question remained, was the life they found truly native? Or had they introduced it during drilling? The uncertainty will never be fully resolved, because once the borehole existed, the lake was no longer pristine. Other teams learned from this. When scientists targeted Lake Whillans, they used a different approach. Hot water drilling instead of mechanical bits. Sterilization protocols more rigorous than surgical standards. Immediate sealing of the borehole after sampling. The contamination was minimized, but not eliminated. It's impossible to eliminate. The act of drilling changes temperature, changes pressure, introduces material. Even sterile water contains modern isotopes that don't match ancient signatures. The question isn't whether we change what we study. We do. Always. The question is whether the change is justified by what we learn. And who gets to decide? The Antarctic Treaty provides framework. Every research proposal must undergo environmental review. Potential impacts must be assessed. Alternatives must be considered. Approval requires consensus among treaty nations. It's a system designed to prevent reckless exploration, to ensure that curiosity is balanced with caution. But the system has limitations. Political pressure can influence decisions. National pride can encourage risky projects. The desire to be first can override better judgment. And once permission is granted, the work proceeds. Even if conditions change, even if new information suggests greater risk than anticipated. The ethics of reaching extend beyond contamination. There's also the question of what happens to the data. Who owns it, who can access it, how it gets used. Under the treaty, scientific findings are supposed to be shared openly. No nation can claim exclusive rights to discoveries made in Antarctica. In practice, this works mostly as intended. Research is published, data is archived, collaboration happens across borders. But not always. Some findings remain proprietary. Some samples are held by individual labs. Some information doesn't get shared until years after collection. The ethics get murky. When public funding supports exploration, but results benefit private institutions. When data that could help predict global climate change is delayed by publication cycles. When samples that should be available to all researchers are controlled by those who collected them. These aren't hypotheticals. They're ongoing tensions that test whether the ideals of the Antarctic Treaty match reality. There's also the question of indigenous knowledge. Though Antarctica has no native human population, it exists within frameworks of understanding beyond Western science. Some cultures view the continent as sacred, as a place that should remain beyond human reach, as a reminder that not everything in the world is meant for us. These perspectives are rarely centered in discussions about Antarctic exploration. The scientific community tends to frame the debate in terms of data versus contamination. But there are other ways to value the ice, ways that don't depend on what we can extract from it. The ethics of reaching require listening to those voices, acknowledging that knowledge isn't the only form of relationship. That restraint can be its own kind of wisdom. Videos like this take time to create. If they help you relax or learn, subscribing helps the channel continue. The challenge is that curiosity doesn't pause for ethics. It wants answers now. It sees an unexplored lake and wants to sample it. It detects unusual chemistry and wants to understand it. The impulse is human, natural, but left unchecked it becomes exploitation, even when the intentions are pure. The history of exploration is filled with examples of places entered too quickly, of ecosystems damaged by well-meaning research, of knowledge gained at costs that only became clear later. Antarctica offers a chance to do better, to prove that we've learned from past mistakes, that we can explore with restraint, that we can value preservation as much as discovery. But it requires constant vigilance. Every proposal must be questioned, every method examined, every assumption challenged, because the ice doesn't forgive mistakes. What we contaminate stays contaminated. What we disturb stays disturbed. There are no do-overs. One approach gaining support is remote sensing, using satellites and surface-based instruments to study subglacial environments without direct contact. The data is less precise, but the impact is minimal. We can detect changes in lake volumes from space, map the flow of water through channels using radar, measure chemical signatures in melt water that seeps to the surface naturally. It's slower, more indirect, but it preserves what it studies. This represents a philosophical shift, from exploration as extraction to exploration as observation, from knowing through touching to knowing through listening. It's not complete knowledge, but it might be ethical knowledge, the kind that respects boundaries, that recognizes some things are valuable precisely because they remain intact. The future of Antarctic research may depend on this shift. As technology improves, remote methods become more powerful. We can see farther through ice, detect smaller changes, infer more from less direct evidence. Eventually, we might understand the subglacial world well enough, without ever needing to drill into it again. That would be success. Not conquering the frontier, but learning to coexist with it, to let it remain itself while still gaining knowledge. The ethics of reaching aren't abstract. They play out in every decision, in choosing whether to extend a borehole another meter, in deciding if one more sample is justified, in weighing the value of data against the cost of obtaining it. These choices don't have clear answers, but making them carefully, thoughtfully, with humility about our impact. That's what separates responsible exploration from harmful intrusion. Antarctica asks us to be better than we've been elsewhere, to prove that curiosity and caution can coexist, that the pursuit of knowledge doesn't require possession, that some mysteries are worth preserving, even if it means never fully solving them. The ice waits beneath our feet, holding its secrets, patient, offering us the chance to approach differently, to reach without grasping, to know without consuming. Whether we accept that challenge, whether we choose ethics over ease, will define our relationship with the last pristine environments on Earth and set the pattern for how we explore beyond it. Silence in Antarctica is never truly empty. Stand still enough and you begin to hear what fills it. The creak of ice adjusting to pressure, the distant crack of a calving glacier, the wind that carries no other sound, and beneath all of it frequencies too low for human ears. The Earth itself humming. Scientists have learned to hear what our bodies can't, using seismometers to detect vibrations that move through ice and rock. The instruments translate motion into data, waves into graphs, and suddenly the silent continent becomes articulate. Every tremor tells a story. Ice quakes reveal where glaciers slip against bedrock. Low-frequency rumbles show where melt water flows. Sharp cracks mark fractures opening in the ice sheet. Collectively, these sounds create a portrait of motion, of a frozen world that's anything but still. The seismic network across Antarctica operates continuously. Sensors placed on the surface and in boreholes, each one listening, recording every vibration, transmitting data back to researchers who analyze the patterns. What emerges is remarkable. The continent breathes, not with lungs, but with the expansion and contraction of ice, with the filling and draining of subglacial lakes, with the slow advance of glaciers toward the sea. Each process creates its own signature sound, its own frequency, and by learning to recognize them, scientists can map what they can't see. When a lake beneath the ice drains, the seismometers detect it, not as a sudden event, but as a gradual change in background vibration. The ice above the lake settles. Stress redistributes. Small tremors increase in frequency. The sound tells them that water is moving, even though the movement happens kilometers below. Hidden from sight. This is exploration through acoustics, understanding through resonance. It's less direct than drilling, less certain than sampling, but it's non-invasive. It leaves no mark. The ice continues its motion undisturbed, while we listen to the story it tells. The technology has improved dramatically. Modern seismometers can detect movements smaller than a nanometer. Changes invisible even under magnification. They register the footsteps of researchers walking nearby, the impact of snowfall, the pulse of ocean waves hitting ice shelves thousands of kilometers away. Everything that moves creates sound, and sound creates data. By analyzing years of recordings, scientists have discovered patterns, seasonal variations in seismic activity, daily cycles corresponding to tidal forces, long-term trends that suggest accelerating change. The ice is getting louder. Not dramatically, but measurably. More cracks, more slips, more motion. The sound of a continent responding to warming, adjusting to stress, revealing through vibration what temperature measurements only hint at. In some regions, the seismic signature has changed completely. Areas that were stable now show constant tremors. Zones that rarely moved now slip regularly. The sound tells researchers where to focus attention, where the ice sheet is most vulnerable, where collapse might begin. This acoustic monitoring extends beyond glaciers. Seismometers also detect impacts. Meteorites striking the ice create distinctive signatures. Sharp spikes followed by echoes as shock waves travel through the frozen mass. By analyzing these impacts, scientists can determine the structure of the ice, how deep it goes, what layers exist within it, where changes occur. Each meteorite becomes an unintended probe, sending signals through the continent, revealing internal architecture. There's something elegant about this approach, using natural events to understand natural structures, requiring no machinery, no drilling, no contamination, just patient listening and careful interpretation. The human voice in Antarctica doesn't carry far, but the voice of the ice travels vast distances. Seismic waves from an earthquake in Chile reach sensors at the South Pole. Vibrations from a volcanic eruption in Indonesia circle the globe. Antarctica receives them all, records them, becomes a witness to planetary motion. This has practical applications. The seismic network contributes to global monitoring systems, helps detect nuclear tests, tracks major earthquakes, monitors volcanic activity. Antarctica isn't isolated. It's connected acoustically to everything, part of a planetary system where vibrations link all continents, where sound travels through rock and water and ice, carrying information across distances. The listening continues day and night. In winter, when human activity stops. In summer, when research stations hum with machinery. The instruments don't sleep. They record constantly, building an archive of sound that stretches across decades. Future researchers will mine this data, looking for patterns we can't yet recognize, for signals buried in what we currently dismiss as noise. The longer the record grows, the more valuable it becomes. A timeline of how the continent sounds, how its voice changes. Researchers describe certain seismic events with something like affection. A particular ice quake that registers every spring. A glacial slip that happens like clockwork. Regular patterns that become familiar, that mark the passage of time in ways human calendars don't capture. The ice has its own schedule, its own rhythm, and listening to it long enough, you begin to sense the patterns, to anticipate what comes next. Not perfectly, but with intuition built from years of attention. Some of the most interesting data comes from the edges, where ice shelves meet ocean, where floating ice flexes with tides. The sounds there are complex, overlapping frequencies, waves hitting from below, ice groaning as it bends, cracks propagating through thickness. The cacophony translates to graphs filled with peaks and valleys, each one a moment of stress, of adjustment, of the ice negotiating with forces it can't resist. These are the sounds of vulnerability, of systems approaching limits, the seismic signature of change. By listening carefully, by comparing current sounds to historical baselines, scientists can predict when an ice shelf might collapse. Not with certainty, but with enough warning to track the process, to understand how it unfolds. The sound precedes the event, gives voice to stress before it becomes visible fracture. This is exploration as prophecy, hearing the future in the tremors of the present. In some ways, the shift to acoustic monitoring represents maturity, a recognition that not everything needs to be touched to be understood. That distance can be its own form of intimacy. That listening is a kind of presence. The ice doesn't require our physical contact to reveal itself. It's been speaking all along. We just needed to learn its language, to build instruments sensitive enough, to spend time enough that patterns emerged. Now the conversation continues. The ice speaks through vibration. We respond through interpretation. And slowly, very slowly, the dialogue builds understanding. The sound of listening is quiet. It's not the roar of machinery or the celebration of discovery. It's the patient accumulation of data, the gradual recognition of pattern, the slow building certainty that what we hear matches what exists. This might be the future of Antarctic exploration. Not drilling and sampling, but sensing and inferring, using the ice's own voice to understand it, letting it reveal itself through sound, through the frequencies it produces, through the way it responds to stress. The continent becomes articulate, not through our questions, but through our willingness to listen. And in that listening, in the hours spent analyzing waveforms, in the years of continuous monitoring, we discover something unexpected, that the ice wants to be understood, not through violation, but through attention, that it's been waiting, patient, for us to develop ears sensitive enough, minds patient enough, to hear what it's always been saying. The sound of listening is the sound of respect, of approaching without demanding, of learning to receive rather than extract. And beneath the South Pole, where the ice is thickest, where the secrets are deepest, that sound continues, quiet, constant, waiting for anyone willing to listen. There's a moment that happens to everyone who spends time thinking about Antarctica. A shift in perspective. You stop seeing the continent as a place to be conquered, and start seeing it as a place that doesn't need conquering, that exists perfectly well without us, that will continue existing long after our attempts to understand it fade. The ice beneath the South Pole keeps its world intact, not through hostility, through simple persistence, through being exactly what it is. Weight and pressure and darkness and cold. None of it designed to resist exploration. All of it naturally creating conditions that make exploration nearly impossible. We've learned extraordinary things. That mountains hide beneath kilometers of ice. That lakes exist where no light reaches. That water flows in channels carved through stone. That life persists in conditions that should prevent it. All of this knowledge came slowly, through decades of careful work, through instruments lost and methods refined, through the patience of people who accepted that answers here don't come quickly. But for all we've learned, the fundamental mystery remains. We still can't truly explore what lies beneath. Not completely. Not without changing it. The ice sets terms we can't yet meet. And perhaps that's fitting. Perhaps some places should remain beyond full reach. Not forever, but for now, until we develop ways to understand that don't require possession. Until we learn that knowing and touching are not the same thing. The continent teaches this. Through every instrument it claims. Through every borehole it seals. Through every signal that fades before returning. It teaches that boundaries are not failures. They're information. They tell us where we are in the long arc of human capability. What we can do now. What we might do later. What might always remain beyond us. And there's peace in that. In accepting that some questions stay open. That some depths stay hidden. That the world doesn't owe us accessibility. As night settles over the ice. As the temperature drops toward extremes. As the stars emerge in that impossibly clear sky. The continent continues its motion. Glaciers flow. Lakes fill and drain. Rivers move in darkness. All of it happening without witness. Without need for acknowledgement. The ice doesn't require our understanding to validate its existence. It simply is. And in being it preserves what we've lost elsewhere. Stillness. Patience. The kind of deep time that makes human urgency feel trivial. Standing on that frozen surface. Knowing what lies beneath. Knowing we can't reach most of it. That knowledge creates humility. The recognition that we're visitors in a place that doesn't accommodate visitors easily. That our presence is temporary. That the ice will outlast our efforts. This isn't defeat. It's perspective. The understanding that exploration has evolved. From planting flags to gathering data. From possession to appreciation. From conquest to coexistence. Antarctica represents that evolution. It asks us to approach differently. To value what we can't fully access. To respect boundaries. To find satisfaction in partial answers. The ice beneath the South Pole will keep its secrets. Not all of them, but enough. Enough to remind us that mystery isn't absence of knowledge. It's acknowledgement of limits. And limits aren't weaknesses. They're definitions of what makes us human. We're curious. We build instruments. We ask questions. But we're also capable of restraint. Of recognizing when pushing further does more harm than good. Of choosing to listen instead of touch. The frozen continent beneath our feet holds more than data. It holds possibility. Not the possibility of extraction, but the possibility that we can change. That we can explore without exploiting. That we can know without consuming. Antarctica waits, patient as always, offering itself as teacher, as mirror, as reminder that the world is larger than our ability to measure it. And in that largeness, in that enduring mystery, lies something worth preserving, not for what we might extract from it someday, but for what it preserves in us. The capacity for wonder, for humility, for approaching the unknown with care rather than certainty. The ice will remain. The darkness beneath will continue. The water will flow, whether we watch or not, whether we understand or not. And perhaps that's the most important discovery of all. That some things exist independent of our attention. That the world continues. Beautiful, ancient, unknowable, exactly as it should be. Thank you for joining this journey into the depths. If these kinds of thoughtful explorations help you relax and reflect, consider subscribing. The mysteries of our planet are endless, and there's always more to discover. By listening, by watching, by learning to approach with open hands instead of grasping ones. The stillness beneath the South Pole's glaciers waits, not for us to solve it, but for us to accept it, to let it be what it is, sealed away, breathing slowly, keeping time on a scale that makes our lives feel like single heartbeats. And in that acceptance, in that gentle release of the need to know everything, we find something unexpected. Peace, the kind that comes from recognizing our place, small but aware, temporary but attentive, part of a world that moves with rhythms deeper than understanding. Rest well. The ice continues its work, and so does the night.